Hello everyone, I'm Vina Ermagan, and I'll give you an overview of the LISP Flow Mapping service in ODL and some of the SDN and NFV use cases that you can leverage it for. Agenda-wise, I'll go over first the original goal for the project when we started, and then how it's implemented, where we are with it in Boron release, and then at the end, we'll go over some of the use cases. And if you have time, I have a small demo of one of the use cases. If you can go over it, we'll do that as well. All right, so with that, the original goal of the project for us was to enable scalable, easily programmable software-defined overlays. And programmable overlays, of course, may be an overloaded term. So to narrow that down, I've listed 4 additional properties or requirements that we wanted to satisfy. First, we wanted to have a data-driven control plane. And what I mean with that is, if you assume that routing in an overlay kind of boils down to knowing the mapping of an overlay address space to the underlay addresses. We want to, instead of pushing all the mappings of this type to all the data plane nodes, we want to actually pool these mappings, or the mappings that are needed based on the traffic that the data plane nodes see in an on-demand fashion. And the goal, the reason for that is mostly to satisfy the scalability requirement. Second, we wanted to have support for its set of transport addresses and forwarding policies. Now IPv4, v6, L2, but also things like NSH and service paths and so on in terms of address spaces, and forwarding policies such as load balancing, multi-homing, traffic engineering, and so on. And I'll go into more detail on that in the next slide. Oh, actually, third, we wanted to have a simple northbound API, and that's to kind of satisfy the simple programmability of the overlay. And lastly, we wanted the control plane to be based on open standards. Now, to see what we mean by multiple address spaces and more importantly, data plane-driven control plane and various forwarding policies, I have a very simplified kind of mock scenario here. Let's assume you have 2 enterprise branches here, A and B, and they're connected using an underlay network, and you want to build an overlay across these 2. In addition to that simple deployment scenario, we have a mapping system up there that stores the mappings of overlay address space to the underlay physical address space. So what we mean by data-driven control plane is that you would basically, well, first, if host A wants to send traffic to host B, you would see the packet going to the first branch router. The router needs to know now where host B is located, so it will query the mapping system. It will get the attachment point address for the site B, and it will encapsulate the packet to there. Destination router will decapsulate and send it to the host. Now let's say we want to support multi-homing. The destination has multiple connections to the network. So how do we do that? We can basically update the mapping and say include the multiple connections or multiple interfaces on the destination in the mapping, and the mapping system would keep track of the routers or data plane nodes that previously were communicating to that destination, that specific destination, and it will notify those data plane nodes that a change in the policy occurred, and then both paths will be used by the router. A more complicated kind of policy, let's say we want traffic to go through an intermediary hop or specify a specific path. We can again go update the mapping for that destination, and mapping system will notify the sources that are talking to that destination and will go through the intermediary hops or the path that is specified. Lastly, let's assume we have a third kind of node that, or a third host that we want to specify a source-based policy for it and say, for this specific source, we don't want to go through the intermediary hop. We want to go directly to the destination. So again, we can update the mapping system and say, okay, this is a new mapping that we have, and the mapping system would notify the sources that are using that destination mapping to enforce the policy. So with that, we've kind of covered the, what we wanted to achieve and the types of policies that we wanted to support. And now let's see how that's actually implemented. So that's the OpenDaylight picture. I'm sure all of you have seen it before. And there we have an implementation of the mapping service. And you can program it via the northbound REST-conf APIs or via other services within OpenDaylight. So for instance, you can program it with Neutron or SFC, meaning basically you use those to define the mappings of the overlay to underlay to the mapping service and the forwarding policies that you want to support. And in order to basically look up those mappings from the data plane, we've implemented the southbound plugin, the LISP southbound plugin, which implements the control plane protocol of LISP. And just by a show of hands, how many of you are familiar with our protocol? Okay, so a few people. But as a to simplify it, basically, it's LISP on the control plane side. It enables a very simple mapping lookup mechanism. So you can send a UDP message to the mapping system and say, where is this end host located, or this virtual IP located, or virtual address can be any kind of type of transport, MAC or so on. And the mapping system will, and then the data plane node accepts responses to that. In terms of examples of data plane nodes or forwarding planes that actually support this protocol, there are many platforms, but examples in the open source are Fido, an open overlay router, which is available on Linux and Android, and OpenWRT. So what do we have actually inside this mapping service? At its core, basically, the mapping system is a data store for mappings, where it enables services, some additional services for specific data types that it supports natively. The most important one of those is longest prefix matching for IP addresses. So you can specify the prefix for a branch office that you have, and then look up specific addresses within that prefix and find the mapping for those. And that's also kind of one of the aspects that enables simple programmability and scalability for this kind of use cases, for the IP-based use cases. Then the mapping service supports two-tuple keys. So you can say, you can define the keys for or overlay addresses based on source and destination. And we saw an example of that earlier in the mock scenario that we were going through. And the source and destination can be IP, MAC, or any other kinds of the data type that we support. And also there's support for kind of three-tuple mappings to support multi-tenancy and segmentation. So the first level would be VNI. And as I mentioned, multiple data types are supported, IP, MAC being some of them, but also NSH or service paths, distinguished names, AS numbers. So a large set of kind of policies and mappings can be implemented natively, but also we support like opaque mappings as well, so you can define your own data types. So this slide kind of captures at a high level the architecture and the internal architecture of the mapping system. And at the core of it, what I want to share here is that we have the mapping system implementation where the data and the mappings are basically persisted using the data store. And also we have an in-memory cache layer for performance and speed. But also what you see is that then we have, of course, the Lisp Southbound plugin. But what you see is that the core of the mapping service is really somewhat generic and independent of the protocols that are used for looking it up. So we have the Lisp Southbound plugin and the Lisp mapping service kind of API to look that up using the Lisp protocol, but you can look it up via, as I said, other services or define other mappings through other services independent of the protocol that you want to use. And of course, we have some easy early stages of neutron support and the northbound API. So in terms of APIs, this is an example of how you would add a mapping. We support RESTconf APIs, and you would want to use RESTconf or basically the pure RESTconf aspect for adding or removing mappings. But in order to get the processed results, such as the longest prefix matching for IP, you have to use the RPC so that we can insert our logic in there and implement those processing parts. This is a list of mappings types or data types that we support. I've already covered some of them, and it's basically here for your reference. I won't go into the details of that, but let's see what's new in Boron. So in Boron, one of the main features that we have is high availability using the clustering of the data store. We also have considerable increase in performance, and test coverage and code quality is also increased. And now with that, I think we can get into the use cases, actually. So I've grouped the use cases into 4 buckets. First, the basic overlay and VPN scenarios. And then we look at the policy-based forwarding scenarios, such as multihoming and traffic engineering. Then we look at use cases that are relevant to the flexible transport. An example of that is IPv6 transition. And lastly, mobility-related use cases, so workload mobility, cloud extension, and so on. So looking at the first bucket, the overlay and VPN type use case is the basis in that sense. And here actually I've included the configuration that you need for setting up a Lisp port on the FIDO platform. And as you see, it's basically just 4 lines of configuration, and you're good to go. The implementation will look up the mapping system on demand and send your traffic to the destination without any additional configuration. Now, there are multiple ways that you can drive an overlay. BGP, for instance, and so on is used in many places. But as you, the point here is that you can see it's very simple to program and configure, and that's to the point, or one of the goals that we mentioned, which was simple programmability of this overlay. Second, let's look at the policy-based, and we talked about multi-homing and load balancing. As you can see here, this is the example that we kind of went through in the beginning, where you have the 2 branches and you want to enable multi-homing, maybe with active backup or maybe with load balancing. And as you can see here, all that you would need to do is to add the policy that you want to support in terms of priority and weights to the mapping system. And the mapping system kind of natively supports these properties. Priority would define the active backup scenario, so if the priority of the two interfaces are the same, then you're using active-active. And the weight is basically the relative load that will be sent over those. So in this case, basically, you're using an active-active scenario, and one of the paths, B2, is having twice as much load. Moving forward, and with the IPv6 transition on the flexible transport that I mentioned. And as you can see here, let's assume that you have the two branches as we discussed before. You have an IPv4 underlay that they're connected over, and maybe you want to move one of your branches or transition one of your branches to an IPv6 core. Considering that you have other branches that are connected to an IPv4 only core. So how you would enable that can be seen here. Basically, all you can do is transition your site to an IPv6 core, and then deploy a router that we call re-encapsulating, enabling a feature that we call re-encapsulating tunnel router on that device, and basically giving it one interface on the v4 and one interface on the v6 network. And then all that needs to be done in terms of programming the overlay is to say that the destination host B is now reached first via the RTR hop, and then the final destination site. And this is again an example that we saw earlier, similar to where we were inserting a C hop to specify a path or intermediary hops to go through. And actually, this is kind of the demo scenario that I wanted to share with you. As you can see in the demo scenario, we're using FIDO platform, and we'll enable a project called Overlay Network Engine on it. And we'll do the transition from the v4 to the v6 network for the destination side, and you'll see that the traffic will go through the intermediary hop from the v4 only connected source to the destination. So with that, let me actually go to the demo and do a quick overview of that. And I'll increase the font as soon as we get everything up and running. And let me select some of the interfaces so that we can see what's going on. Let's see. Okay. All right, so, and we're running Open Daylight here as well. Now let's see what will happen. So essentially, as I was showing the deployment scenario, we have the two branches, and we're just doing a ping between them. But you can see that the mappings are being fetched with request messages from the mapping system. They get the responses, and they start doing the communication. Now, what we'll do is basically update the mappings, and as you can see here, and the demo is fully scripted, so let me make this a bit bigger. It's fully scripted, but we're basically here just adding the mappings, inserting that intermediary hop into the mapping service via the REST API. And what we see is that the mapping service will signal both of the branches with the change in forwarding policy, and so they'll get the new mappings. And now, if you start the ping, you'll see that, and the reason that you're seeing multiple requests here is that the interfaces that I'm capturing, some messages are seen on both, so you see some replications, but essentially we've modified the forwarding policy for the source, saying that the traffic has to go to the new hop this time. And if you dig in, you can see the different bits of the overlay encapsulation that is for the destination side we're sending to the intermediary hop as it's explained here. And you'll see the priorities and weights properties that we discussed. Okay, so the good thing about this demo is that it's fully scripted, and we have step-by-step kind of tutorial for you to try it at home and so on. It should take less than 10 minutes to set everything up, install, and run the demo. And you'll see the pointer to the wiki with the instructions on the last slide. All right, so going back. Okay. So lastly, these are some of the open source platforms that support the protocol, the LISP protocol, and we've tested for interoperability with the mapping service. So you can go to their website, download the code, and play with them. First, I mean, you've seen the Open Daylight case that we just went through. We have the mapping service implementation and the LISP plugin there. We have an implementation of both the data plane and control plane. Well, the control plane to talk to the Open Daylight, but also as a first basis, we have the VXLAN GP or LISP GP and cap support in FIDO, and that's what the demo was using. And then there's also the Open Overlay Router, which has implementations of data plane and control plane over Linux, OpenWRT, and Android. So you can run it on your phone as well. And you saw the Wireshark integration. Okay, and with that, you'll see that we have the list of references, both for Open Daylight and for the FIDO. The tutorial or the demo that I just showed is available here. I'll put the slides up online. Feel free to go look at it, and hopefully you can run the same demo within 10 minutes.
Where will you put the slides?
I think they will be available online on the Open Daylight, so you should get an email at the end of the conference for where they will be. But also, actually, I'll put them up on the wiki for the Open Daylight LISP Flow Mapping project as well.
You can load them into the scheduling tool right now.
Sorry?
You can load it into the scheduling tool.
Oh, yes.
And then everyone can get it.
Okay, yeah, absolutely.
So you don't need to wait for the people.
Okay, sure, yeah. I'll put it online right after the talk on the wiki, and then also I think you can go and check it if you go to the schedule. Okay, and with that, I think we are done. If there are any questions, I would be happy to answer. Yes?
The neutron DVR is very complicated. I'm thinking about we can use LISP to implement DVI.
Implement DVI.
DVI is distributed router in the neutron.
Well, in the neutron.
DVR. Distributed virtual router.
Right. DVR. Okay. Yes. So you could, and we have some. Well, we have some preliminary implementation of neutron in Open Daylight already, where we get the neutron calls. We insert the mapping of, let's say, the virtual, the VM's IP address or MAC to the host that it's running on, the address for the host, the server. And with that, any other point in your overlay or in your OpenStack network can basically look it up and send traffic to. So that's what the preliminary version supports now. But we're hopefully going to have some more resources to spend on that for the Carbon release to make that more comprehensive.
So what's the project you implement in network?
So the one that is available now is not in NetVirt. It's within the LISP Flow Mapping service itself. we have some code that gets the neutron. We subscribe to the neutron calls. We get the neutron port create and so on. The provisioning part is not enabled yet, and that's what I was saying. Maybe in the next releases we'll have time to enable that. But it's just the kind of the routing and the overlay information that we're getting from the neutron call. So when a port is created, we get the VM IP address to the host server IP address, and we put that in the mapping service. So other VMs can reach it using that information if you're using the LISP protocol or control plane, or your ports are basically using the overlay network engine within FIDO. There are projects in FIDO, and I don't know if you were in the tutorial earlier today, earlier in the conference on Monday, the FIDO tutorial. So there are some projects there that are enabling neutron integration for setting up the ports and so on. And the plan is to kind of work with those projects. I think Jerome is working on one to integrate the one project on FIDO into those basically. So and they're not using NetVert actually. So they're for instance, one example is using etcd. It's putting the neutron calls and the journaling there, and then it has an agent on the host where it gets the calls from etcd updates, and then it provisions the FIDO locally. So that's one option. The other is we have netconf support using Honeycomb project within FIDO. So we could use netconf to configure the ports and so on, and set up the network for the provisioning side. Sure. Anything else? I think yeah, go ahead.
One question.
Sure.
So you're using the LISP as a control protocol for
Yes.
set up the tunnel.
Yes.
So compared with actually this tunnel can be reset up or download, just download the locator. So what's the major reason you use LISP as a control?
Right. So for the provisioning, for the pre-provisioning of the ports or tunnels or even the mappings, sure, I think anything like you can use netconf to pre-provision and that's it. The reason to use the LISP protocol is for a quick way to do the on-demand, to fetch the on-demand mappings. So if you do pre-provisioning, you're assuming that you know always ahead of time all the destinations that this VM may want to talk to. And if that's the case, you can use netconf to pre-provision. And the FIDO platform, for instance, supports Honeycomb. You can provision it, and the overlay network engine there that we're working on has support for pre-provisioning the mappings or destinations that you want to talk to. But for the cases where you can't in advance know all the destinations that the VM wants to talk to, then you, and also for scalability reasons and so on, you would want for some of the destinations to be fetched on demand as the traffic flows, if you're not aware of the traffic patterns in advance. So that would be what you would use the quick lookup protocol. Okay. All right. Thank you. Everyone, and I'll put the slides online right after the talk.